The push-up is the most primitive, universal exercise in human history. To build upper body strength, you don't need weights, machines, or a gym membership. You just need the floor. Across generations, from basic middle school gym classes to elite military boot camps, this single movement has served as the undisputed baseline of physical fitness. But because it requires zero equipment and seems so simple, most people treat the mechanics with a dangerous level of casualness. They drop to the ground and approach it purely as an isolated chest and arm workout. That narrow focus leads to a cascade of mechanical failures. You'll routinely see hands turned inward, elbows flared out at 90 degrees, and lower backs sagging downward. These specific breaks in posture actively limit muscle growth while introducing immense shear stress into the shoulder capsules and lumbar spine, accumulating microscopic joint damage with every single repetition. To understand why those slight misalignments are so disastrous, we have to peel back the skin and look at the physical architecture of the movement. When you observe the internal mechanics, the push-up reveals itself as a highly complex, full-body kinetic chain where every joint from your neck to your ankles must lock perfectly into place. During the upward phase, the pectoralis major and triceps brachii act as prime movers. These muscles drive horizontal adduction of the shoulder, pulling arms toward the midline, and extension of the elbow. This is where the flared elbow mistake becomes critical. Biomechanics dictate a strict 60-degree rule. Flaring past 60 degrees forces the shoulder into severe internal rotation. Under load, this compressed position grinds rotator cuff tendons against bone, leading directly to impingement. Electromyography research shows that this wider, flared position actually results in significantly less chest muscle activation. By cutting the movement short, you're sacrificing both strength and range of motion. To achieve structural perfection, simply plant your hands just outside shoulder width and actively screw your palms into the floor. This effectively tucks your elbows to a safe 45-degree angle, forming a tight, powerful arrow shape with your upper body. While your chest and arms push the load, a hidden network of stabilizer muscles must work to keep your shoulder blades anchored and tracking safely. Beneath the chest lie the serratus anterior and pectoralis minor. During the press, these tissues act as guy wires for your scapula. As you lock out at the top, they pull the shoulder blades forward, achieving full scapular protraction. Moving down the kinetic chain, the lower body requires a rigid isometric lock to maintain the integrity of the movement. The baseline state of a perfect push-up is a moving plank. Your primary resistance isn't an external weight. It is the massive gravitational pull acting directly on the center of your torso. To neutralize gravity, the deep transverse abdominis, your gluteus maximus, and your quadriceps must all fire isometrically, holding the spine in a rigid, neutral line. If any part of that lower body lock fails, the spine sags. The physical force generated by your upper body leaks out through your core before it can ever be translated into the ground. A perfect structural form turns the push-up into a customizable machine governed by the laws of physics. We can calculate the exact intensity of your workout using ground reaction force. By treating the body as a lever, we can determine precisely what percentage of your body weight acts as the physical load. In a standard push-up, your hands support 64% of your total body weight. Shortening the lever by dropping to your knees reduces that load to 49%. Elevating your feet onto a 24-inch box shifts your center of mass forward, increasing the mathematical load to 74% of your body weight. You can also manipulate hand placement to hack the body's internal anatomy for targeted muscle activation. Bringing the hands into a narrow base under the center of the chest eliminates the biomechanical leverage of the larger pectoral muscles. This shift forces a massive spike in force generation from the triceps brachii, which must work significantly harder to extend the elbow. For advanced stability training, suspension devices like TRX rings remove the stable floor entirely, introducing multidirectional instability. This data comparing traditional and suspension push-ups confirms the impact. The instability forces the anterior deltoid and the triceps to fire at significantly higher levels to protect the spine and shoulder joints. Mastering these levers, joint angles, and muscle synergies allows you to recalibrate the push-up for nearly any fitness goal, anywhere you can find a few feet of floor.